We are delighted to have Charlotte Lyddon from the University of Liverpool. I'll just let some more people in that have just joined us so they don't miss the introduction. Charlotte is a lecturer in coastal dynamics at the University of Liverpool, and her research is targeted towards a better understanding of the drivers of coastal and estuarine hazards for improved awareness of hazard mitigation and public safety. She's interested in how numerical models can be used and improved to better understand complex coastal and estuarine processes, and that's from developing process-based models to better simulate how drivers of flooding coincide and interact in estuaries, to using downscaled physical constants and hydrological and marine climate predictions to assess future changes to estuarine water quality. Her research engages end users by providing essential information for observational records, model sensitivity tests, and what-if scenarios to inform hazard assessments and alternative management scenarios. I think that's what we're going to hear a bit more about today. So, Charlotte, over to you.
Thanks, Jonathan. Those are maybe 3 quite long sentences that I ended up sharing with you. Okay, hi everyone. Hopefully you can all see that and that you can all hear me okay. Yeah, thank you so much for having me. I'm really pleased to be here today to be able to present to you some of the research that I've been working on for the last 3 or 4 years that's mainly focused on exploring the dynamics of compound flooding, what's happened in the past, what's happening at the moment, and what's going to happen, we think, into the future using a range of instrumental observation data, hydrodynamic modelling tools and climate projections. The work is supported by a very large team of collaborators, and I'm going to be talking to you mainly about 2 different projects today. One which was a UK climate resilience project working with colleagues at Bangor University, BGS, University of Hull, and then an ongoing project working with the Environment Agency called INVEST. So coastal and estuarine flooding occurs when extreme sea or river levels exceed a local threshold, such as a sea defence, and that results in inundation. It represents the most dangerous and costly hazard facing estuaries, and it's the 2nd highest hazard to civil emergency in the UK, the highest being pandemic influenza. And globally, it's caused more than 3 million deaths since 1700. And in the UK, it causes in excess of £540 million in annual damages. So compound flooding is driven by extreme sea levels and river discharge occurring at the same time or in very close succession. So 2 drivers which may not necessarily be extreme on their own can combine to amplify their impacts. The combined drivers can exceed a threshold and then subsequently cause flooding. So the video you can see on screen at the moment shows the progression of atmospheric pressure at the bottom and rainfall on the top as a storm passes over the UK. And this storm brings both a drop in pressure, which can raise sea levels, and an increase in precipitation that can increase river discharge at the same time to cause compound flooding. And so on the right-hand side of the screen, we can see our hydrograph in blue, which can be used to describe a river flood event in more detail based on its width, steepness and magnitude. We can look at the lag time between the peaks in the 2 drivers, and generally the closer together or the shorter the lag time, the more compound maybe the event will be. So I'm going to show you a few sort of different packages of research, I suppose, that I've done to develop process understanding and the impacts of compound flooding. So this first one aims to understand how can we best investigate compound flooding? How can we use historic data better to understand how, where and when compound flooding could occur? So we used river discharge measurements or observations at 15-minute frequency, and we took these from 126 gauges across the UK. These are shown by the orange dots on the figure that you're looking at the moment. So I wanted to use gauges which had a river discharge that exceeded 50 cumecs, but also had a long enough record, so from between 1984 to 2013. And we used the most downstream non-tidal gauges on each river. And this river discharge data was paired with observational total water level from the nearest tide gauge. These are shown on the blue stars on screen to better represent our coastal processes. So we then used or calculated skew surge, shown by the figure in the bottom left, used as a measure of extreme sea levels. And this is the difference between our maximum observed and predicted water levels over one tidal cycle. So the sub-daily 15-minute data was used for the river discharge in a peaks over threshold analysis to identify the magnitude and relative timing of extreme river and sea level events. So all peaks shown by the red dots here, which exceeded a threshold, were isolated for the analysis to primarily identify the biggest and most prominent peaks and to account for seasonality. We then used what we call the hydrograph duration, or a hydrograph window, which is set around each river discharge peak exceeding the threshold. And the maximum surge within that window is assigned to the river peak. So in the Conway, which this figure is an example of, our average hydrograph duration across the whole record was calculated and shown to be 20 hours. So the maximum skew surge within this window around the peak is then paired with our river discharge. So with these pairs of river discharge and skew surge, we looked at dependence using a correlation coefficient, the number of times that both drivers exceed an extreme threshold each year, and then also looking at lag times as well. So the extreme river and sea level pairs were used in a Kendall's rank correlation test. This analysis has been shown before, it's been done before, but always using daily mean river discharge. So the 15-minute frequency discharge data that we're using here provides an improved assessment of dependence and an ability to calculate that time lag. So the correlation tests tell us more about the chance of those most extremes occurring or coinciding. So what we see from the figure here is that the strongest correlations are seen on the west coast of the UK compared to the east coast. The west coast is more likely to have high surge and river flow events. The catchments are more mountainous, they're more flashy here, and they feel the effects of sort of Atlantic storms that pass across them. And then we also looked at the average number of times per year that both skew surge and river discharge are extreme in a storm season. So when both of these drivers exceed the 95th percentile. So what we see from this figure is that you see the most number of times that drivers are extreme in the northwest of England and west coast of Scotland. But interestingly, what we see is that there are apparently less storms in the southwest than the northwest, but we still show that there's a high correlation from the figure on the left. So a high correlation doesn't necessarily mean that more extremes are occurring. We also use those lag times to look at whether or not we thought those two peaks of sea level and river discharge were likely to overlap. So what we can see on the figure here is the duration of an overlap that we calculated, with red dots indicating there's less chance of compound flooding occurring, and green dots indicate more of a chance of compound flooding occurring. But overall, we combined these three parameters, or proxies, I suppose, for compound flooding, and applied a series of thresholds to them. So catchments which show a stronger correlation, where you see more, or where you're likely to see more events or extreme events happening per year, and where the time lapse are going to more likely cause compound flooding, gives us this figure here showing 36 estuaries across the UK, largely on the west coast, where there is a potential for compound flooding events to occur. So the Lune comes out from our analysis as being the most vulnerable to compound flooding. So this sort of analysis can be used to identify where agencies, for example, need to focus additional monitoring or where additional modelling would be helpful to support hazard assessment. So we show that sub-daily data can be really useful to analyse compound flooding, but don't just rely on correlations. And we also show 36 gauges that are identified as being potentially vulnerable to compound flooding. But then we sort of asked ourselves, well, how do we actually know if those locations really experience flooding in reality? So this leads on to the second package of work, where we look at using historic records of flooding to help understand where compound flooding has happened before. Are the historic records sufficient? And also, are we able to establish thresholds for compound fluvial or tidal flooding in these systems? We use the Conway Estuary in North Wales as a case study for this paper. So the Environment Agency and Natural Resource Wales across the two countries provide polygons, shape files of flood extent. These polygons can include information on start date, end date of flooding, and basic information on what maybe the sources of the flooding would be. So we took this data for the Conway Estuary, specifically the lower estuary shown here, and there were 12 records of flooding in the lower estuary, but unfortunately only 6 had data available from the tide gauge and river gauge, so observation data on those records. But if we take a look at 2 of them just quickly as an example, the polygons shown here shows flooding through the centre of the Conway. This is from November 1980. Picked out here in the red line is our sea level or total water level. We've got maybe not a very big surge, maybe 20 or 30 centimetres, and a river discharge of around 400 cumecs with a lag time of just under 6 hours. And then we come sort of close to present day, an event from 2015. The polygon is a car park in Clamroost, shown by the purple outline just in the bottom here. But what we can see is that the river discharge and peak in sea level occur much closer together. Our river discharge is nearly 800 cumecs. Our skew surge is just under half a metre. So this is a compound event. And there are photographs, videos, news articles to indicate to us that flooding did happen on this date. So start to plot up the data for these 6 recorded flood events. These are shown through the stars. To orientate you on the figure, we've got the magnitude of river discharge for each event along the x-axis, magnitude of the sea level on the y-axis for each event. The black dot, or the black square, sorry, indicates our magnitude of predicted tide at that time. And so then the vertical black line then indicates the magnitude of the skew surge on top of it. And the colour of the stars indicates the lag time. So colleagues who work at Bangor University know, and we sort of said to ourselves, there must be more than 6 times that this very flashy mountainous catchment has flooded. There's got to be more data to tell us that flooding has happened than these 6 events. So the key limitation of using sort of records such as this is that not all flooding events have necessarily been documented, and there are gaps in the record. So we then went back to the river discharge data, and I added the top 50 river discharge events on record and their paired sea level. So they're shown by the circles. And then added on top of that the top 50 extreme sea level events and their paired river discharge levels. And what we can start to see is, if we've got the dates of those 6 events, we can then start to build up a picture that actually there are more events that are likely to have caused flooding this event down in the bottom right, the orange circle, which is about 900 cumex, the most extreme river discharge on record. We've got some very high sea level events up here as well, and started to think to myself, okay, well, maybe some of these caused flooding. So I Googled the events, the dates of the events that sit around sort of the outer limits of this figure. And as you can see, these did all cause some degree of flooding. We can see Storm Kira, February 2020, this yellow circle here, a significant event that we know had impacts across the UK. So what we want to be able to do by building up this bigger picture is understand if we can start to set thresholds for when flooding happens, and using a combination of our observation data and historic records, can we make these more accurate? But rather than me sitting on Google by hand searching all of these dates, we used web scraping to search for whether or not these additional top 50 sea level and top 50 river discharge events did or didn't cause flooding. So the date of each event was entered into one of 4 search engines, and results were tagged based on what the results of the search engines told us, whether reports from local agencies, local authorities, news reports could indicate if there was a high river discharge, if they mentioned a storm surge, if they mentioned high tide. Most of them mentioned a degree of storminess, so this is maybe a slightly more generic term, but one that we found was more commonly used. Interestingly, there are 3 events where the tagging didn't indicate that any flooding had happened, but they're starred. So Natural Resource Wales tell us flooding happened, but the internet is telling us it's not. And that's because these all really occur before the internet was a thing. So pre-internet flooding events are not really captured in these analysis. And then we've also got an area in the middle of this figure, in the middle of this figure around here, where it's very messy. It would be very difficult to put a threshold here. There are conditions that are very similar, which some do cause flooding and some don't. So here we use a numerical process-based flood model, ECSA list flood, a 2D diffusive wave model, to simulate flooding in the Conway, to see if we can use a model to fill in those gaps from the observation record and the record of online sources. So we used a digital elevation model here, interpolated to 20 meters with flood heights included, validated to gauges through the estuary, and we ran a series of simulations, a sensitivity test, I suppose, consisting of 520 scenarios. We did a series of 3 different scenarios, but for the purpose of today, I'm just going to show one, to test the influence of the relative drivers of estuary flooding. So how does the magnitude of total water level, storm surge, river discharge, and time lag influence the flooding we see? So simulations consisted of 40 river discharges combined with 13 incrementally increasing tidal levels. So we went from, for sea levels, from a neap tide increasing in 20 centimetres to as close to the spring tide as we could get, with a design storm surge superimposed on top of it. So the Environment Agency provide design storm surges, and this was scaled up to a magnitude of 1.03 metres, which was the level of the biggest skew surge on record. And our idealised hydrographs were given a gradient based on the average gradient of the hydrograph we see in the record, and scaled from 25 to 1,000 cumex, increasing by 25 each turn. And all of the peaks aligned. So our peaks in sea level, surge and river discharge all aligned. So for this scenario that I'm showing today, there's a 0-hour time lag. For the observation records, we found that the hydrograph generally occurs 3 hours before the peak of water level. So that is another scenario that we tested, but I'm just not showing it here. So we use flood area to describe the flooding from each scenario, defined as a function of our river discharge, sea level, surge type, and time lag. And each test scenario was compared to a baseline, which was taken from mid-January 2016, which is a scenario we found that caused the river to fill up, but not overtop its banks. So all of the results are in comparison to how much extra flooding do the scenarios cause compared to this full channel baseline. So these are the 520 simulations. Each box represents one of the simulations. So the colour scale indicates flood area compared to the baseline. Red creates more flooding. The dashed lines, contours, are added here to connect cells that show a similar amount of flood area. Some cells or scenarios down in the bottom left here, they cause no flooding. But as we move kind of to the top left of the figure, we can start to interpret things like the colour change, the gradient, shape and separation of the contours can be interpreted to explain the dynamics of flooding. So the contour gradients change across the range of simulations as the flooding becomes more or less sensitive to one driver or another. So in the top left, there's a sort of extreme equal influence of drivers causing flooding here. We then have scenarios that there's a predominantly fluvial influence or a predominantly tidal influence. That's, I suppose, to be expected. The area of interest really is in the middle here for us, which is where on our web scraping we saw that sensitivity as well. And what we're looking at here is between the 4 and 5 kilometre squared contours is we move from a concave contour to a convex contour. So this middle section where we move to a more convex contour indicates we're interpreting it as a compound flood effect, where the addition of both drivers amplifies that flood area. So the contours were then superimposed on the web scraping activity that I showed earlier. The first thing I'm going to do is colour those events that we know did actually cause flooding to occur to, oh no, sorry, I've done that wrong. They have already been changed to blue. So our events that web scraping said didn't cause flooding actually do. And this area of sensitivity in the middle is confirmed by the model. But really what this is showing us is the thresholds are more of a yes-no. It shows us across the whole estuary whether flooding does or doesn't occur. So actually, how useful is a threshold that's just a yes-no? What about a threshold for when the flooding actually impacts people? So we start to set more site-specific thresholds for flooding to show the conditions that cause flooding to occur at different sites through the estuary. So we chose 4 separate locations, examples such as a school in Conway, farmland in the sort of lower estuary, a railway in the mid-estuary, and sort of dwellings in the upper sections of the estuary. And for each of these locations, we then show in black or white from the 520 simulations, which simulations do or don't cause flooding at each area, to sort of show the codependence between these drivers at each location. We can see in the upper and lower estuary, there's either predominantly a tidal or fluvial influence. In these locations, a single variable flood probability would be sufficient to calculate the likelihood of flooding occurring, so using just tide, sea level, or river discharge. But in the middle section is where it's interesting. You start to see flooding under a much wider range of sea level and river discharge combinations. And so in these areas of the estuary, a joint probability analysis is much more important when you're looking to assess flood likelihood. So have records been have floods been well documented? Well, we show that records are incomplete, and we can fill these in with instrumental and model data. And can we establish driver thresholds? Yes, we think we can, using gauge and model data together. We use the model to explore flood dynamics and show sensitivity to different drivers. We show where in the estuary and under what conditions you need to account for the compoundness of the drivers. But we also show that although we want general rules for how to better manage flooding across catchments, in estuaries such as the Conway, that's incredibly challenging. And we show that you need joint probability in some areas to account for flooding, but maybe not everywhere. So we've looked a lot about what's happened in the past, but we also want to think about what is going to happen with compound flooding next into the future. So in recent years, here we've got the Dyfi estuary on the west coast of Wales, shown in the top figure, but across Wales, they're seeing an increasing amount of rain. The news reports are starting to acknowledge some of these drivers of flooding and name them in write-ups of events. So here, Wales's mountainous topography means lower river catchments bear the brunt of floods. So literature tells us that climate change is likely to increase the regularity of these types of events, but also amplify the magnitude of them. And we wanted to explore how much climate change could influence compound flooding. Will it become more of a problem, and how? And should we account for this change in future incident and management strategies? So we use for the first time hourly projections of future sea level, storm surge and river flow to assess changes in the magnitude, codependence and timing of storm-driven compound flooding events. We use the Dyfi estuary as a case study here. We're testing this methodology on one estuary based on previous analysis to show it's vulnerable to compound flooding, but also based on the fact that creating sub-daily projections of river discharge is incredibly challenging. And we've been working with colleagues at Bristol University who have created projections for the Dyfi estuary. So it's a case study based on the fact that this data is not easily available. We know that we have to use sub-daily data to best represent hydrograph dynamics in an estuary. So at the moment, this is the only sub-daily river discharge projection we're aware of in the UK. So we're using it, and that's why we're using it in the Dyfi. So we used 12 downscaled perturbed parameter ensembles that at a later point I might call a PPE. That means an ensemble member for the high emissions scenario, RCP 8.5, from a global climate model. We use HADGEM 3. So the hourly continuous climate data was used to force marine projections, shown on the left, and then also used to force a convection permitting model, which was then used to force a hydrological model to provide us with our river discharges. And then we then use this analysis to feed into an inundation model. So we split the continuous data up into 3 time slices. The sea level data was continuous. The hydrological projections were in these time slices. So we worked the time slices available, which represent baseline, near future and far future conditions. So we first of all compared quantiles, percentiles of these different ensembles across the 3 time slices. So we averaged across the 12 PPEs or ensemble members so that we can account for the uncertainty of each. But what we show, first of all, is that we don't show a great change in how we think that storm surges are likely to change into the future. That's largely in line with literature. But we do show that there could be more of a change in the return periods. into the future. So we're able to show that into the far future, for example, a 1 in 20 year surge is expected to increase only by 3 centimetres, but it will change from being a 1 in 28 year event, a 3/4 of a metre surge, to more like a 1 in 23 year event. So maybe not the huge magnitude of change that we would expect to see in other drivers of change, but we're much more likely to see more extreme river discharges up to 2080. And this is where we see much more noticeable changes. So we can see the outliers are around sort of 1200 cumex, but I'm going to zoom in to the box whisker at a much lower magnitude. So we can start to see that although our means maybe go down slightly, our 75th percentiles, our more extreme river discharges, are increasing. And from the return periods, we start to see that a 1 in, oh, sorry, that green line should be across 1 in 20. Our 1 in 20 year event, imagine that green line is here. Our discharge increases under a 1 in 20 year event. And for 600 cumex, that goes from being a 1 in 17 year event down to a 1 in 4 event. So a much more substantial change into the future. But then I ran a kind of similar analysis to that I showed in the first section of the talk from the observation data to start to look at doing a peaks over threshold analysis on our river discharge and sea level to start to see how these drivers will change into the future. So first of all, looking at how dependence between our two drivers are likely to change. What is the chance of the most extreme drivers coinciding, and how often are the drivers both extreme? So A and B here. So the drivers appear to be becoming more dependent. They're becoming more extreme more often. That's the figure in the middle. And the peaks appear to be, at least by the end of the century, occurring much closer together. So we're showing that under climate change, compound events are becoming more compound-like. So the effects of this compoundness is likely to be amplified into the future. And we then use this analysis to provide forcing conditions that are representative of different conditions into the future to force a flood inundation model to show how these changes may create an increase, I suppose, in the flood footprint in an estuary. So we use as a baseline present day baseline conditions for a 1 in 50 event. That's shown by the grey outline, the grey area. Then for a 1 in 20 year event into the far future, nearer the end of the century, with maximum sea level, we show by the kind of lighter orange. And then we show that flooding can increase even more into the future, potentially under a 1 in 50 year event with maximum sea level as well. So those more extreme conditions that are likely to happen more often will be causing a greater degree of flooding. So this package of work represents a novel use of physically consistent hydrological and marine projections in estuaries. Fluvial drivers of flooding are projected to exhibit greater changes in the magnitude compared to marine drivers, where skew surge slightly less so. We show there could be an increased dependence and reduced lag time, which could amplify future flood hazard in the Dovey estuary. And again, reiterate that joint probability and dependence between these drivers should be incorporated into flood hazards assessments into the future. But estuaries aren't just vulnerable to the impact of flooding. I've done a lot of work on flooding recently, but what we acknowledge is that many important environmental services and unique ecosystems provided by estuaries are also impacted by water quality. And this this project that I'm now looking at is part of an Environment Agency project looking to address an evidence gap on how and where water quality might change in our estuaries into the future. So our ability to implement climate adaptation methods to minimise, I suppose, the impacts of future climate change on water quality is critical. So this project, called the INVEST project, is looking at investigating the vulnerability of estuarine water quality to climate change, and it sets out to answer 3 key questions. So how will climate stresses to estuaries change this century? How will these changes in the stresses impact estuarine water quality? And which estuaries are most vulnerable to water quality degradation? And where might adaptation strategies be most effective? So as before, we're using that same sort of pattern of downscaling from a global climate model to downscaled sea level, marine and precipitation and hydrological projections, using 12 ensembles for the high emissions RCP 8.5 scenario from HADGEM 3, and again using these hourly continuous climate data or sub-daily temporal resolution to really capture those processes. But rather than just focusing on the Dovey, we're now scaling up to complete this analysis for 75 estuaries across England. So for our marine projections, here we can see the grid from the AMM7 NEMO model, which is the model developed and run by and published by John Tinker at the Met Office. We have on the map here the black dots, which are showing those 75 English estuaries as defined by the transitional water bodies within the Water Framework Directive. But what you'll notice is a lot of those black dots actually sit within what the model classes as land. So, for example, around the southeast and the northwest. So then, in fact, what we have to do is take the nearest grid cell location that's shown by the red dot. So that's largely the kind of nearest coastal grid cell that we take our projections from the model. And that's sea level, which comprises of a tide and a storm surge, and then sea surface salinity and temperature, and sea bottom salinity and temperature. Our hydrological projections are again being run by a team at Bristol University, but will be provided to us in due course. The project is ongoing, so a lot of the analysis so far has focused on looking at the stresses to water quality from, I suppose, the marine end of our estuaries. So as an example, looking at how sea surface temperature might change into the future, the coloured lines here indicate each of those 12 ensemble members, and from each ensemble member, each individual coloured line, we take the average maximum, then we average that annual maximum across all 12 ensembles and take the ensemble mean, that's the thick black line, put a trend line through it, that's the red line, and then look at the slope of that line. And then we do that at every estuary that we're looking at across the UK, and we can see on the right hand side here that we see between 0.05 and 0.07 degrees of warming in our sea surface temperature each year. And we're specifically seeing in the northeast of England, our estuaries there are seeing a particularly large degree of warming. This is in line with recent literature showing that the North Sea is warming twice as fast, nearly, as some other oceans and seas. So this kind of analysis has implications for algal blooms, for example, but also analysing from our marine projections things like heat waves, droughts, the occurrence of flash floods, and both high and low flow scenarios. So a lot of the previous analysis that I've just shown looks much more at those high flow extreme scenarios that are likely to cause thresholds to be exceeded. But when it comes to water quality, we're much more interested in those lower flow scenarios. And then combined with that, we're also building 7 regional models to better understand present and future estuarine processes. These are shown here on screen, and at the moment we've got 3 set up so far, largely across the West Coast. And these will be run in 3D. So we've got here a kind of flexible mesh shown to run in 3D in Delft. But the outputs from each of these sort of, I suppose, more intense numerical models will be compared to simpler estuary box models to evaluate, is a 3D model in some of our estuaries needed, or would a 2D box model be sufficient to represent, for example, residence time? So the simpler models can then be and will hopefully be used to forecast future conditions under a high greenhouse gas, so that RCP 8.5 climate scenario, to try and simulate how temperature, salinity and residence time, which will each impact water quality, could change into the future. And so the process of validation is somewhat more complex for models simulating salinity and temperature. We use sparse observations. So, for example, in the Ribble, there were 2 observation points in time across these 2 points to validate the model to. And I think you'll agree that even though there are only 2, it still looks pretty good. Our model simulation, the line, goes straight through the observation point. We also have observation data from CFAS, shown here, where a sort of darker colour indicates where the model is maybe either overestimating or underestimating salinity. The model does pretty well at predicting salinity in the more offshore areas. So work at the moment is trying to figure out why the Lyddon, just in the South Lake District, is doing such a bad job of predicting salinity, and why maybe the Ribble or the Wyre are overestimating it as well. But so as an example from the Northwest, we're using the regional models at the moment to simulate estuary residence times. So running a sensitivity test with idealized conditions. So we used boundary conditions, which was an M2 and S2 tide, an idealized constant river flow shown on the x-axis, with releases into each estuary changing relative to the tidal state. And this is shown for the Wyre, just as a close-up. And we're showing here how residence time under these different tidal conditions, it's the residence time for when our tracer is released relative to neap tide, or on a spring tide, or flood or ebb tide. So what we can see here is that under 5 cumecs of river discharge, residence time does vary dependent on release time. Residence time is longer under lower flows, so sort of a justification for why our analysis of hydrological projections wants to look at lower flow scenarios. But residence time is less sensitive to release relative to the tidal condition under much higher flows. But comparing this to the estuaries across the Northwest, some are more vulnerable to the magnitude of river discharge. Residence time is more sensitive, not vulnerable, I'd say sensitive, more sensitive to the magnitude of river discharge and tidal condition of release. So those which show maybe slightly less sensitivity, we think could be because of the shape of the estuary, the width of the mouth, and those which show greater sensitivity are much narrower estuaries. So potentially the shape of the estuary having an influence on it there. So not really any answers to this work at the moment. Hydrological projections are incoming, but the findings will be collated into a single mapping platform for England to hopefully translate information on those kind of on water quality for baseline, near future and far future scenarios, so it can be a sort of central database for communication. And that will help us to identify which estuaries are most vulnerable to changes in water quality, and be able to identify maybe when and where things that need to be managed will happen as well. But overall, I've shown hopefully that hazard assessments need to incorporate joint probability and interdependence between marine and fluvial drivers now and into the future. There's a critical need for physically consistent, appropriately downscaled coastal and fluvial projections that will future-proof flood management strategies in the coming decades. The methodologies that I've shown here are scalable to estuaries worldwide, but really that is largely dependent on where sub-daily data and sub-mesoscale river and sea level observation or projection data is available, as long as the projections are forced by the same overall global climate model, so that the same processes are driving that level of change. If you'd like to chat more, I would love to chat more. Please feel free to send me an email and a few acknowledgements of who we're working with and the funding as well. But thanks so much for your time, and very happy to answer any questions as well.
Great. Well, thank you, Charlotte. It seems like you're certainly very busy. There's lots of really interesting work there. If there are any questions, then please feel free to put them in the chat or raise your hand to ask them. Give it a minute and see if anyone's got any burning questions. It seems to me like sort of the key take-home message that I took from your presentation was really the need for a proper integrated sort of catchment to coast approach. I don't know if you want to comment any more on that.
Yeah, and it's really challenging, because the question we mainly get asked, or sort of what managers or agencies I think are really looking for, are much more general rules about how do you manage flooding in estuaries, and how can rules or sort of approaches be applied to multiple estuaries. But really, because the drivers of change and also the estuaries themselves are so variable, and as we show, flooding within that estuary as well is so variable, that really, unfortunately, and it is always going to be maybe the more challenging approach, is that you need in-depth analysis for each estuary that you're looking at. I think what we're trying to do with the regional models in the INVEST project, looking at water quality, is because we're trying to look at all estuaries, which is a big job, but we're going to try and do it, is see if there are patterns and trends between similar sized estuaries. Are there any characteristics of an estuary that can help us to say, like the width of the mouth, this is more or less vulnerable to a change in residence time, for example. So it's, I suppose, the next job for us is scaling up our methods to see if we can pick out those rules that are maybe more useful to apply in management, but that also address kind of the researcher's interest in being very site specific. And it's challenging. You can't run it's impossible to run a 3D model for every estuary around the UK. It's computationally expensive. So what maybe the box models, these 2D kind of representations of the estuary, are the better way to go. So yeah, it's an interesting thing to think about, is how do you balance the two.
Mm-hmm. And like you say, every estuary is different. You know, geomorphologically, hydrological point of view, land use. You know, there's tidal influence. It's all very, very different.
Yeah, for sure. And we don't capture this at all in our analysis, but the use of these estuaries will change into the future as well. I mean, especially in the UK, they're sites of extremely important infrastructure, energy infrastructure, ports, harbours, maritime heritage as well. That will influence as well how they operate.
Oh, absolutely. Mike, you've got your hand up.
Thanks, Jonathan. Thanks, Charlotte. That was really interesting. Just taking those last 2 points, and you talked about principles and manipulating estuary shape and that sort of thing, which I guess we've been doing, but really on a piecemeal basis. Can I take it back up into the catchment? Because now, I guess, in many catchments, the Natural Resources Wales, the Environment Agency, SEPA, they're trying to manipulate the headwaters in order to try and sort of, slow down runoff, change the runoff patterns, open up areas, hold water storage, even bringing beavers in order to control it. So it's whether or not they've got any principle, whether they're doing that on a piecemeal basis or whether they've got a set of principles that you could, for these headwaters, that you can then, or not you, but it's out of your fields, but they can map onto what you're doing.
Yeah, absolutely. It's something that we've spoken about as to how we could make kind of additional use of the models, really, is can we start to, we've spoken about it in a sort of a flood water accommodation perspective of are there areas where you could make strategic breaches during a flood event to, I suppose, help reduce the volume of water within the channel or within certain areas to, I suppose, divert the water away. And the models could certainly help that. And I suppose that we're not clear maybe at the moment as to how those strategies being applied further up the catchment could have a mitigation effect for compound events. I suppose the idea of slow the flow would, in this context, extend that lag time. So it could certainly help to, I suppose, stretch out the time when their estuary is almost overwhelmed with a huge volume of water. And a lot of the time, well, in the Conway especially, the flooding really happens because as the tide comes in, it creates this backwater effect where the river discharge just, it's blocked from getting out.
Yeah.
So if the river discharge doesn't reach the lower estuary until maybe the ebb tide rather than the peak of high water or even the flood tide, that could certainly help with sort of water being removed from the estuary. So sorry, carry on.
No, that's right. I think it's, I mean, talking to people in the Environment Agency and Natural Resources Wales, it's that sort of level where what they're trying to do is manipulate things even over a few hours. Give them that, to allow the hold back the water enough time before you've gone past high tide, and then the estuary can deal with it a bit more. So it's that I guess a smart way of dealing with that. I noticed one of your collaborators, Tom Coulthard in Hull, he's one of my colleagues. One of his PhD students, who again was one of my assistants, Shona Thompson. She was trying to model the catchment areas, really bolting them onto the part that you're doing, sort of thing. Now she wasn't working in this country. I think she was places in Africa that she was working, but there are those. So it's as Jonathan started saying, it's actually starting to bolt models together and look at the whole system, which is good. But that's good. That's great. Thanks.
No, it's interesting. It's a good point. And I suppose how much those manipulations slow down the flow will need to vary in each estuary as well. So again, maybe coming back to the earlier point that you maybe couldn't just say, oh yeah, well, definitely putting some beavers in here will help to mitigate compound flooding. It might for one estuary, but it may not for another.
Yeah.
So yeah, but interesting point. And I suppose maybe bringing in hydrological models as well, or precipitation models to show how water doesn't just move through the channel from the upper estuary, but maybe down the sides of the catchments as well. It's about building models that better represent our systems as well.
That's great.
Yeah, cool. Okay. Thank you for your question. Thank you.
Many thanks. Thanks a lot.
Great, thanks, Mike. We have had a question come in on the chat, Charlotte. I presume you can see the chat.
Okay. I can, yes. Yeah, let me have a look.
Oh, actually, no, it's a question for me. Yes, we are recording.
Yes,
and the recording will go onto our YouTube channel. And I can make that available. Absolutely.
Cool.
Okay, no, we do have a question.
Hi, Cheyenne.
Can you hear me?
Yeah, I can, yes.
Great talk. So in some of your slides, you were showing that the compound flooding historically mostly happened in the Western Estuaries in the UK, where it is mountainous. And in maybe some future slides, you say that the compoundless will increase in the future. I can't remember if we have mentioned whether the compoundless also increase in Eastern Estuaries or only in Western Estuaries.
Great question. That is what we're hoping to answer with this current project with the Environment Agency, where we're scaling up the work to the 75 English estuaries. So because at the moment we've only got the hydrological projections for the Dovey estuary, we can only do that future compound flood analysis in the Dovey, but we're moving towards doing it for many more estuaries around the UK as those hydrological projections come into us. We're going to be starting doing a bit of analysis using Jamie Hannaford's E-flag projections. They're daily mean projections for river discharge. So they're not quite the temporal resolution that we'd be looking ideally to be using, but they'd certainly be good for some of the bigger estuaries where maybe the hydrograph duration is longer than a day. But they hopefully will give a good indication of, yeah, even just like a heat map showing where compound flooding will be changing. My expectation, having not done any of the analysis yet, is that it would mainly still be in the northwest, where we're likely to see more of a change because of mainly a change in the precipitation and the characteristics of the intense convective rainfall that will drive more extreme river discharges. But that's an unproven hypothesis.
Yeah, because you never know, right? Like in the future, the patterns and characteristics of the storms might also change in the eastern parts.
Yes,
so,
yeah, I think what we're maybe seeing is that the east of the UK will see much more vulnerability and change in salinity and temperature of the water, and the west coast will see more changes in the magnitude of flows and storm surges.
Yeah.
Okay. But yeah, I'll chat to you when we've got the results.
Great, thank you.
Okay, great. Okay, Heather, we've got time for one very quick question, if that's okay.
Yeah, sure.
Okay, Charlotte, that was an absolutely brilliant talk. I am apologising because I missed the start of it. And I'm not sure if you're aware, but in Northern Ireland, we have a series of catchment to coastal models. And I started to write it and then thought it'll be quicker to say it. So I know I'm speaking really quickly. We don't use them for floods yet. It's more for like source apportionment. So a lot of it was actually funded by Northern Ireland Water because we only have one regulator in Northern Ireland. And so just to make you aware of that, and it'd be really lovely to be able to follow up with you because I really enjoyed your talk. And there's a lot of things you're doing that we've done as well. And we've looked at the hydrology and the routing of the river, of the contaminants and things through the rivers, because my main aim is shellfish. So I think there might be some really nice synergies, and I really enjoyed the talk. So thank you very much. And I'll shut up, Jonathan.
Oh no, thanks so much. Yeah, Ireland is a glaring omission from our work at the moment. It's something that we're looking to expand into at some point. So yeah, please do drop me an email.
Perfect, thank you.
Great.
And that's also a nice little lead-in because I put the link to the YouTube channel in the chat, so anyone that missed the start can catch up. I hope to get that uploaded later today, if not, it'll be tomorrow. So that is that's all we've got time for today. So thank you, Charlotte, once again. Lots of interesting discussion there as well, and links to take things forward. Our next talk will be on the 5th of December, and will be given by Craig Smeaton from St Andrews, who will be discussing carbon storage in fjords. So I hope you can join us for that. We also have the programme coming together for the new year, and all information will be on our website. So hopefully you can join us for those, and if not, the recordings will also be available on the YouTube channel. So thank you, everyone, and enjoy the rest of your day.
Thanks, everyone. Cheers. Cheers, Jonathan.
Thank you.